Alright, welcome to this video on rates. What we're going to be looking at first is just what is a rate, then we're going to be looking at average rates, and then we're going to be looking at instantaneous rates. So let's get into it. What is a rate exactly? Well, essentially the answer is whenever you see the word per between two values. So example, you could be talking about an apple costs 50 cents per apple, so that's like an example of dollars per like apple, so dollars versus amount of something. Or you could often you buy vegetables more like dollars per kilo. Or a different rate could be talking about speed, where you cover a certain number of kilometers every hour, so that's kilometers per hour, so that's a rate as well. Okay, let's have a look at one of those. Let's look at a speed one, like a driving one. So let's suppose someone's taking a bit of a trip, so here they are in the car, and at a certain time, let's call it time 0 to kick us off. Let's say they're at point 0, so they're where they are is 0 kilometers along the road. They've just started their trip. Okay, and they're driving along. And after, say, 1 hour, so time is now 1 hour, they're now 60 kilometers from where they started. Then, after another hour, so time is now 2 hours, and they have now driven 120 kilometers in their car. Alright, so that's the situation. Let's draw that on a set of axes to investigate it further. So here we'll have time in kilometers along our horizontal axis, and we'll have distance in kilometers along our vertical axis. So when time is 0, they start at point 0, right here at the origin. Then after 1 hour, they've gone 60 kilometers. There they are. And after another hour, so time is 2 hours, they've gone 120 kilometers. So that up there is 120. There's the next point. And there's our line. Cool. So if we want to know what the rate is, so we're trying to find the rate. And so our answer is going to be in kilometers per hour. We already kind of know that. But what we're really looking for here is actually the gradient of this line. Gradient. And the reason it's the gradient is that the gradient is the rise over the run. So gradient is rise over run, where the rise is the change in our vertical axis. Oops. So obviously that's going to be 120 kilometers. So, alright, so the rise is the change in kilometers, which is obviously 120, and the run is our 2 hours that have gone past in that time. So our run is our change in time, which is 2 hours. So 120 divided by 2 gives us 60. So our rate here is 60 kilometers per hour, which is pretty obvious all along, really. Okay, so you can also notice that our rate, or the speed this person's traveling, is constant. And we know this because our line is linear. So we know that this line here is linear, which means a constant rate is happening. Constant rate for a linear line. So you can see that the gradient along that entire line is always the same. Okay, let's look at another example that's a little bit different, a little bit more challenging perhaps. So there's another car going on a different journey. Here's the graph that describes their journey. Here's time in, let's change it now to minutes, and here's distance. This time we'll make distance in, let's say, meters this time. Oh no, we'll make time seconds. Okay, so time is in seconds, distance is in meters, so it's going to be a much shorter trip, obviously. Okay, let's say that they start from the start. Okay, so time equals 0, they're at the start, and first off they cover ground really quickly. They make lots of distance, very steep gradient going on here, and then they slow down a little bit, so they're still going forwards, but they've slowed down until getting here. And let's say the whole trip took them, let's say, the whole trip took them 10 seconds. Alright, maybe it's a quick start at some lights or something, and they've gone really fast here, but then they've slowed down once they've approached the speed limit. Maybe that's what happened. So after their 10 seconds, let's suppose they managed to travel 500 meters. Okay, let's check this point out here. So that might be only after 4 seconds. They had already traveled 400 of their meters. Okay, so you can see that the rate here, this rate is quite large because it's steep. So that rate large because of steep gradients. Steep gradient. Okay, so in other words, what's going on here is their speed is fast in that region. Okay, fast. Over here, however, the gradient is less steep. Gradient is less steep. So that means they are going slower. And you'll notice that here the gradient's a little bit steeper than over here. So that means they're actually slowing down as well. Okie dokie. Now, another thing you might be interested in, well, what is their average speed? Average speed. Or in other words, their average rate. So remember, whenever this is just an example, whenever you see speed, you're just thinking rate of kilometers, or in this case it's actually meters per second. Alright, well let's look at their average speed. So average speed you could think of maybe as like their average gradient. Or in other words, we're taking a line that goes from their start point to their end point. Okay, pretend that was a straight line there. Okay, so the rate changes. So let's put in a line from the start to the finish. So the average speed is kind of the average gradient, if you like. Average gradient, which is going to be given by the change in x over change in t. Okay, so change in meters, they made it 500 meters, and the whole trip took them 10 seconds. So overall, their average speed is 50 meters per second. Okay, hopefully that's reasonably easy. Okay, however, so 50 meters per second is their average speed. That's how fast they were going on average. But sometimes we're interested also in how fast they were going at a particular time. In other words, sorry about that. In other words, what did their speedo say at a particular time? So, what if we wanted to know what their actual speed was right here? Well, the way we might do that is to draw in what's called a tangent line. It's a line that touches the same point and has the same gradient at that particular point. So this might be a tangent line here, has the same gradient at this point and touches the line just at that point. So then you could use, various points on that line. So there might be this one here, take that point, and maybe it passes through this one here. So this one might be at 1 second and say 1 and 0. So that's a 1, 0. Oh, whoops, wrong way around. 1, 0 points, and this one here is a 4, 500. So if we want to find the instantaneous speed at that point there, it would be 500 take away 0 over 4 take away 1, which is 500 over 3. And you could then solve that on your calculator also. And you would find that that's much higher than 50 meters per second. So, there we go, there's instantaneous rate and average rate for you. So let's do a very, very, very quick recap. Let's do a new graph to just recap this. Okay, so you've got any quantity down here. So this time we might be doing, let's say, we're buying something, so it's costing a certain amount of dollars per kilo. And we might have a very strange sort of arrangement that looks like, perhaps it looks like this. Oh, actually, bad idea. Perhaps it looks like this. Okay, so if we wanted to find our, average price, we'd be using this point here and this point here. So let's put some values in. Kilograms, 2 kilos, costing us, I don't know, $25 maybe. So we'd use these 2 points. And so we'd find the rise, the change in dollars over change in kilo, rise over run, well, kilos, and that would give us 25 over 2, which would be $12.5 per kilo. And that would be our average rate. However, if we want to do instantaneous rate at, say, this point here, we'd draw in a tangent line. There's our tangent line, and then we'd find the gradient of that tangent line, and that would be our instantaneous rate there. Okay, last thing with this rate stuff for now. One more example using our average rate. This one's going to be a bit more sort of vaguely theoretical. Okay, so let's just have that axis as x and this one as y, sort of like normal if you like. And we'll have a graph that looks a little bit like this, where this point can be 2, and let's say that this line actually has an equation of y equals x squared plus 2. Okay, so that'll mean this bit here might be at 3, and then we've got 3 squared, 9 plus 2, so that point will be 11 here. So this point is 2, 11. Excellent. Now, cool, so there's our equation. Let me actually look at writing this equation in function notation. So I'll say that it's the function of x, this sort of abbreviated function notation, x squared plus 2. Okay, now if I want to find the average rate, and it's going to be in y per x, or y per x, if you like to write it that way. So it's going to be the change in y over the change in x, because it's the gradient, it's the average. So we're talking about doing a straight line from here to here. Okay, this point is 0, making that point 0, 2. Okay, so we're talking about average here. Now, one way we can actually do this is by saying, well, let's create our 2 points here, this one and this one. Let's say that this is our point on the x-axis. Let's say that it was point A, and let's call this point B. That means to find what this point here was, we could have done our function of A. So we could have written that point, this point here is actually 2 is the function of A. It just so happens to be that the function of A gives 2, and this 11 point up here, that's the function of our number B. It turns out to be 11. So another way we could have written this formula here is the change in y is our function of B, which is 11, take away the function of A, divided by B minus A, to get this change in here. Okay, so let's check how that works out. Okay, so let's suppose that A is 0 and B is 3. Let's fill everything in for A equals 0 and B equals 3. So our function of B is going to be, well, replace our x squared with b's. So it's going to be, now it's going to be like b squared plus 2. take away function of a, so that's a squared. Take away a squared, whoops, a squared plus 2 divided by b minus a. So let's write that out. We've got a b squared plus 2 minus a squared minus 2 over b minus a. Now in this example you can see that the 2 and the minus 2 are going to cancel out, just giving us b squared minus a squared over b minus a. And in this case our b is 3, a is 0, so we've got 3 squared minus 0 squared over 3 minus 0, which will give us 9 over 3, which equals 3. So our answer is 3 in that example. So this is actually, right now this is not particularly useful, but later on this method of doing things will become extremely useful. And you'll see why later on. Okay, so best of luck. You are now equipped to finish the textbook up to the end of 8E. Best of luck.